Who can draw the house of Santa Claus without lifting the pen? Like Got it. Yeah, this is what continuity is about. So a continuous function can be drawn without lifting the pen, which means we are looking at a function of this sort which we can draw without lifting the pen. But how can we define this mathematically? Well, we are using limits. So here's a definition. A function f is continuous at a if the limit at x goes to a f of x equals f of a. And a function which is defined near a but it is not continuous is called discontinuous. So let's look back at continuity, because this entails quite a lot of information. So I wrote this down here. So this formula in the box here actually implies that f of a is defined, first of all. Secondly, that the limit as x goes to a f of x exists. And then they must be equal. Let's look at one example. It's the example of drug contents in the blood. This is a curve which shows the drug concentration in the blood of a patient, and every 4 hours the patient gets a new injection so that the blood concentration rises again to a high level, and then over the 4 hours it kind of decays in the body and is used, and then there's another injection, etc. We have injections at those times 8 and 4 and 12, etc. And then the drug concentration in the blood rises from a low level to a high level. So the blue curve does not look like a curve which I can draw without lifting the pen. It seems like I have to lift the pen at each of these jumps. And so we would expect that this function is not continuous, at least in some points. To study this a little bit more systematically, I show you 4 examples right at once, and in the next slides I will discuss each of the examples individually. But let's look first at the pictures here. The first function a is f of x is x squared minus x minus 2 divided by x minus 2. This is not defined at 2, which is indicated through the open circle right here in the graph. The next curve here, this goes to infinity as x approaches 0, but at 0 itself we have the value equal to 1. And the third curve, again, this point is taken out of the curve, but is replaced by this point, so that f of 2 is equal to 1. And then here we seem to jump from 0 to 1. So this all look like situations where it is discontinuous, and this is true, which we will show in a second. But also these discontinuities have different qualities to them. So let's look at one after the other. So the first example is this function, which is not defined at 2, and so it has a hole in the middle. So we have that the limit as x approaches 2, f of x, this in fact exists. You can take a left-sided limit and a right-sided limit and you get the same number. What the number is, I'll tell you in a second. But for now, we just are sufficient that we know this does indeed exist. However, f at 2 does not exist, is not defined. So which means they are not the same. Which means the function f cannot be continuous at 2. So f is discontinuous at 2. Now this discontinuity has a special name. We call it a removable discontinuity. Removable discontinuity? Well, this kind of implies we can remove it. So how can we remove it? Well, by replacing the missing value by an appropriate value. So what is the right value that should be put in there? For that we look at the limit now for serious. So we look at the limit x goes to 2 of f of x, which is equal to the limit x squared minus x minus 2 divided by x minus 2. So this equals limit as x goes to 2. The numerator can be factored. So this is x minus 2 times x plus 1 divided by x minus 2. And if x is not equal to 2, we can cancel this factor here. So what we keep, then this limit is equal to the limit as x goes to 2 of x plus 1. And now this is a perfect valid limit, which is equal to 3. So to remove the discontinuity, we should do the following. We should define, let's call it maybe g of x. That would be x squared minus x minus 2 divided by x minus 2 for x is non-equal to 2. And then we can define it as 3 for x is equal to 2. And so then the function g has the discontinuity removed. G would be continuous at 2, f is not continuous at 2. Next example. Here's example b, where the function goes to infinity as x approaches 0, but the value f at 0 is equal to 1. So this exists, but the limits do not exist. Limit x goes to 0, f of x is plus infinity, so it does not exist. So which means f is discontinuous at this point. Now this discontinuity has a special name as well. Well, how would you call it? Well, infinite discontinuity. It has an infinite discontinuity at 0. In the next example, we have the same function as before, but now the value at 2 is replaced by 1. Well, which is also again clearly not continuous. So the limit as x goes to 2, f of x, we computed already, this is 3. And this is not equal to f at 2. So discontinuous at 2. And of course this is a removable discontinuity because we can move this 1 point up. The last example was the Heaviside function. So this function h of t, which jumps from 0 to 1, is called Heaviside function. H at 0 is equal to 1, so there's no problem. Also the left-sided and the right-sided limit exists. The left-sided limit is equal to 0. The right-sided limit is equal to 1, and they are not the same. Which means h is discontinuous at 0. Thank you. We call this a jump discontinuity. Okay, let's look at our drug problem again and see what kind of discontinuities we have here. Again, this is a curve with the drug contents in the blood. We identified the discontinuities at 4, 8, 12, and 16 already. And these are all of jump form, right? So these are jump discontinuities. Bang, bang. Now let's look at one-sided continuity. A function is continuous from the right if the right-sided limit exists and is equal to f of a. So for example, this function here would be continuous from the right if the value at the jump belongs kind of to the right branch. This is x. A function is continuous from the left if it's the opposite, so it belongs to the lower branch here in this graph. And then a function is continuous on an interval if it is continuous in the middle and on the interval boundaries. If they are part of the interval, then the function is one-sided continuous at such an endpoint. So for example, this point, and then the curve, and then this point. So a counterexample, what is not continuous, would be like a graph which starts here, but then at the endpoint it has a different value. So this would not be continuous on an interval. Let's look at one-sided continuity for the drug contents. So we know already at this point it is discontinuous, but maybe it is one-sided continuous, and of course it is. You can come from the left and you approach this point. So it is continuous from the left at the point 12, and also at the point 4 and 8 and 16, etc. This example is also interesting to look for continuity on an interval. So maybe let's look at the interval between 4 and 8 here. So let's call this maybe A and B. And so we know it is left-sided continuous at A, but it is not right-sided continuous at 4. So this means the function is continuous on the interval A, B. You see where I use the open bracket on the left to indicate A is not included, and I can use a closing bracket in B because it is continuous with respect to b from the left, but it is not continuous with respect to a from the right. So maybe as an extra note. So let me summarize. A continuous function can be drawn without lifting your hand. A function is continuous at a, which we define by a limit expression. If the limit x to a f of x exists and equals f at a. A function can be continuous from the left, continuous from the right, continuous in an interval. Now if it is not, then we have discontinuities, and they can be classified even. So we have a removable discontinuity, that was a function which has a hole in it, for example. We can have jump discontinuities, which are a function that jumps from one point to the next. And finally, we can have infinite discontinuities, which are functions which go to infinity and maybe come from infinity and have a vertical asymptote. Oh my goodness. Do I want to ask? I don't want to ask. I'm not asking. No, I don't want to know. Okay, I do want to know. Gerlo, what are you up to? You're drawing a continuous function without lifting your hand. Very funny.